In this lecture, I'm going to be talking about another approach for sentence embedding. So I'm going to be focusing on this paper in 2020 on the sentence embeddings from pre-trained language models. Pre-trained contextual representations like BERT have achieved great success in natural language processing. However, the sentence embeddings from pre-trained language models without fine-tuning have been found to poorly capture semantic meaning of sentences. So in this paper, we argue that the semantic information in the BERT embeddings is not fully exploited. We first reveal the theoretical connection between the mask language and model pre-training objective and the semantic similarity task theoretically, and then analyze the BERT sentence embeddings empirically. We find that BERT always induces a non-smooth anisotropic semantic space of sentences, which harms its performance of semantic similarity. To address this issue, we propose to transform the anisotropic sentence embedding distribution. We transform this distribution to a smooth isotropic Gaussian distribution. So from anisotropic distribution, we go to isotropic Gaussian distribution. But how can we do this? Just using normalizing flows that are learned with an unsupervised objective. Because normalizing flows and many of these generative models are part of unsupervised learning. To encode a sentence into a fixed length vector with BERT, it is convention to either compute an average of context embeddings in the last few layers of the BERT, or extract context embedding at position of CLS token. Of course, there is a third way, and you can use convolution over the hidden layers of BERT, which is more profound. But they demonstrate that such BERT embeddings lag behind the state-of-the-art sentence embedding in terms of semantic similarity. So in this data set, BERT sentence embeddings are even less competitive to the average glove, which is very bad. So note that as demonstrated by this paper, averaging context embeddings, I think this paper is SBERT by this professor, and she introduced SBERT in this paper, and I've explained it before. So unless mentioned otherwise, we use average of context embeddings as BERT sentence embedding and do not distinguish them in the rest of the paper. There is a connection between semantic similarity and BERT pre-training. So we consider sequence of tokens, and to capture bidirectional context during pre-training, BERT proposes a mask language modeling, this MLM objective, which instead factorizes the probability of noisy reconstruction, and X hat is just a corrupted sentence, and X bar here is the mask token. So both language model and mask language model can be reduced to modeling the conditional distribution of a token given this context. So let's talk about co-occurrence statistics as the proxy for semantic similarity. Instead of directly analyzing this term, we consider this term a dot product between a context embedding and a word embedding. So in a well-trained language model, this dot product can be approximated like this. We approximate this dot product. And this PMI, there are many papers on this PMI, which is point-wise mutual information. And log here is a word specific term, and lambda c here is context specific term, context specific. PMI captures how frequently two events co-occur more than if they independently occur. Note that co-occurrence statistic is typically a tool to deal with semantics in a computational way. And PMI is a common mathematical surrogate to approximate the word-level semantic similarity. Therefore, roughly speaking, it is semantically meaningful to compute the dot product between a context embedding and a word embedding. Higher order co-occurrence statistics is context semantic similarity. During pre-training, the semantic relationship between two contexts could be inferred and reinforced with their connections to words. To be specific, if both contexts C and C prime co-occur with the same word, the two contexts are likely to share similar semantic meaning. During the training dynamics when C and omega occur at the same time, the embeddings are encouraged to be closer to each other, while the embeddings are encouraged to be away from each other due to normalization. So these are higher order context co-occurrence that could also be inferred and propagated during pre-training. To investigate the underlying problem of the failure, because BERT sentence embedding without fine-tuning, as I said, is unsatisfactory. So to deal with this failure, we use word embeddings as a surrogate between because words and context share the same embedding space. If word embeddings exhibit some misleading properties, the context embedding will also be problematic. So anisotropic means word embeddings occupy a narrow cone. So everything is inside, and we miss other parts of the state space, and we miss uniformity and many other things. So word frequency biases the embedding space. This is observation one. We expect embedding induces similarity to be consistent to semantic similarity. If embeddings are distributed in different regions according to frequency statistics, the induced similarity is not useful anymore. And they prove that under some assumptions, the optimal embeddings of non-appear tokens in transformer language models can be extremely far away from the origin. To verify this hypothesis, we compute the mean L2 distance between the BERT embeddings and the origin. So we observe the high-frequency words are close to the origin, while low-frequency words are far away from the origin. This observation indicates that the word embedding can be biased to word frequency. Because word embeddings play a role of connecting context embedding during training, context embedding might be misled by the word frequency information, and its preserved semantic information can be corrupted. Though nothing is perfect, we should combine different ideas. The second observation is that low-frequency words disperse sparsely. And we observe that in the learned anisotropic embedding space, high-frequency words concentrate densely and low-frequency words disperse sparsely. This observation is achieved by computing the mean L2 distance of word embeddings to their k-nearest neighbors. In the lower half of Table 1, we observed that the embeddings of the low-frequency words tend to be farther to their k-nearest neighbor and compared to the embeddings of the high-frequency words. This demonstrates that low-frequency words tends to disperse sparsely. So due to this sparsity, many holes could be formed around low-frequency word embedding in the embedding space, where the semantic meaning can be poorly defined. Embedded sentence embeddings are produced by averaging the context embedding, which is convexity preserving operation. However, the whole violates the convexity of the embedding space, and this is a common problem in the context of representation learning. So this is an illustration of our proposed flow-based calibration. As we promised, we mapped it to a Gaussian probability distribution from this probability distribution, which is very anisotropic, but we map it to something which is isotropic. So you know about Gaussian latent space and all of these, so I skipped this. The good thing about probability of density of Gaussian is that there are no whole areas which are poorly defined in terms of probability, and the helpfulness of Gaussian prior for mitigating the whole problem has been widely observed in existing literature of deep latent models. All of these are very important articles. And this is a flow-based generative. If you are familiar with these flow-based generative models, then you can skip this. It's just a mapping. And the generative story of a model is just if it draws Z from this probability, it's a prior distribution. And F here is just invertible transform. It's not just any transformation. It's an invertible transformation. With the change of variables, the probabilistic density function of the observation X could be related. So we learn a flow-based generative model by maximizing the likelihood of generating Baird sentence embedding from a standard Gaussian latent variable. The base distribution PZ, this one is a standard Gaussian, and we consider the extracted Baird sentence embedding as the observed space. And we maximize the likelihood of use marginal by this equation in a fully unsupervised way. So D denotes a dataset, in other words, the collection of sentences. Note that during training, only the flow parameters are optimized, while the Baird parameters remained unchanged. Eventually, we learn an invertible mapping function which can transform each Baird sentence embedding into a latent Gaussian representation. And this invertible mapping is parameterized as a neural network. So this article in 2018 is very important, GLOW. So I just recall these normalizing flows and those things. It transforms a source distribution into a target distribution. But we cleverly choose bijective variable transformations. All of them are bijective. So the result is bijective. So flow-based model is a stacked sequence of many invertible transformation layers. Each transformation is an additive coupling layer, which can be mathematically formulated like this. But this term can be parameterized with a deep neural network for the sake of expressiveness. And we clip the maximum sequence length to 64 to reduce the cost of GPU memory. And we use this NLI dataset for fine-tuning of CMEs at BERT. So their baseline, their implementation is based on this paper, as I said, and they tune hyperparameters, so with 2 levels and coupling width of 32. For coupling architecture, they use 3-layer convolutional neural network, but with residual connection. So it's a scatter plot of sentence pairs, and the sentence pairs with edit distance less than 4 are highlighted with green. So these have edit distance with less than 4. Edit distance with less than 4. These areas, because it's less than 4, and you can compare the flow induced. We have you can compare the distribution of the similarity. We have many things, but in BERT it's just anisotropy, because it is anisotropic. So you're just in a particular space. Their similarity are not uniformly distributed.